welcome back. So, this is lecture 23 in this course on Bayesian data analysis for behavioral sciences. So, the topic of today's lecture is how do we build Bayesian modeling workflow in R. Okay. So, in the previous lecture, I discussed the whole workflow of model building in the Bayesian framework. So, there were 5-6 steps in Bayesian model building. So, we discussed them one by one, and in this lecture we will see how to implement those steps of Bayesian modeling workflow in R. Okay. So, just to recap, what were the steps in Bayesian model building? I will start with the summary of that Bayesian workflow. Okay. So, suppose you are interested in modeling a task, let's say acceptability judgment task, right? We discussed this example in last couple of lectures. So, acceptability judgment task. What happens in this task is this, that the reader or the participant sees a sentence on a screen. Okay. So, for example, they see a boy stole the basket. Okay. So, the participant sees a sentence on the screen and their goal is to judge whether the sentence they are seeing on a screen is acceptable or not. Okay. Whether it is a good sentence of English or not. Okay. So, you can give instructions in any way you want depending on what you want to investigate, right. But the goal is to judge whether this is an acceptable sentence in language English or not. Okay. So, they will respond with a yes and no, yes or no using some keyboard keys, right. So, let us say we are interested in recording that out of total 50 trials. So, let us say when they see total 50 sentences, then in how many cases their response is correct. So, we are interested in recording number of correct responses out of total 50 trials. Okay. So, each time they would give a response. So, let us say this is trial ID here, their response and whether it is correct or not. So, each time in each trial they would give some response either yes or no. Okay. So, let us say they give a response yes in trial 1, no in trial 2, no in trial 3, yes in trial 4 and so on. And this response could be either correct or no or incorrect, right. So, let us say when it is correct we will write 1, when it is incorrect we will write 0. Okay. So, let us say the correctness in each trial is given by 1 1 1 0 0. We are interested in sum of correct responses, a total number of correct responses out of total 50 trials. Okay. So, this is the experiment and this is what we want to model. We want to model number of correct responses. What does that mean? We want to figure out that what is the underlying cognitive process that produces n number of correct responses. Let us call it let us say n. Okay. Number of correct responses in this particular experiment. So, what is the underlying cognitive process f that produces the observed number of correct responses in this particular experiment, right. So, let us say this function underlying cognitive process is f with parameter theta. So, our goal, so the goal of statistical inference here is to figure out what is f, what is this function, what is this underlying cognitive process f which generates the observed number of correct responses. Okay. Also, not just f, exactly what value of theta as well. Okay. So, we want to figure out this thing, what is this function f, what is the underlying generative process f and what is the underlying true value of this parameter theta, okay, that produces the observed number of correct responses. Okay. Now, how do we do this in the Bayesian framework? So, in the Bayesian framework we do it like this. So, we do not know there is some true cognitive process that is producing, let us say your data is this, that x number of correct responses out of total 50 trials. So, x correct responses are observed, right. We do not know what is this true generative process. So, we assume that this observed number of correct responses comes from an underlying distribution f of theta. Okay. And then given this data, we estimate theta. We estimate posterior distribution of theta and also given our prior assumptions about theta. Okay. We estimate posterior distribution of theta, and then we say that if this data is generated by f of theta, then the likely value of theta is theta hat, right. Basically, we get a distribution, not just a single value. And also we compare it with a competing assumption, let us say g of phi. So, the same data could be generated by a competing assumption, let us say g of phi. Then we estimate, given this data, we estimate what would be phi, let us say phi hat. So, posterior distribution of phi, and then we compare f of theta hat versus g of phi hat. So, which one of these processes is more likely to generate this data? So, whichever process is more likely, let us say f of theta hat is more likely, we would say that f of theta hat is closer to the true generative process compared to g of phi. Okay. So, this is how we make inference, right. So, what is the whole Bayesian modeling workflow in order to achieve this inference, right. So, in the Bayesian framework, what we do is this. Let us say n is the observed number of correct responses, right. We assume that the observed number of correct responses, let us say, comes from some underlying generative process, and we need to make some reasonable assumption here. So, we make an assumption, let us say underlying generative process is binomial. You can make a different assumption as well, right, that is up to you. But this is a reasonable assumption to make here, that the number of observed responses, number of correct responses comes from a binomial distribution, where theta is the probability of producing a correct response in each trial, in ith trial. Okay. We call this the likelihood assumption. Okay. So, we start with assumptions. The first assumption we make is about the likelihood. Basically, it is assumption about the underlying generative process. Okay. So, this is the first assumption we make. Then we also make prior assumptions. Okay. So, we make assumptions about the parameter theta. So, what could be the underlying true distribution of theta? So, let us say we decided that theta is p of theta, or maybe more specific, let us say theta has distribution beta 90-10 or something. Okay. So, this is our prior belief or prior assumption about theta. Okay. So, this prior assumption could depend on many factors. We will discuss them later in next lecture, but idea here is to make some prior assumption about theta. Okay. So, how do we make this prior assumption, that we will see later on. Okay. So, this is actually the first step of Bayesian modeling. So, basically we specify our assumptions, or you can say we specify our model. So, we are writing the model basically. So, the set of likelihood assumption and prior assumptions make your model. So, that is your model. Okay. Now, second step that you can do, I mean it's not entirely critical for the Bayesian workflow, but it's a very good habit to always do the second step, which is this, that you can check validity of your priors, not validity, but whether your priors are reasonable or not. Okay. So, you can check how good are your priors, right. So, this is called prior predictive check. Okay. What does this mean? Under these prior assumptions, what kind of data your model will generate. Okay. And that is an important check to ensure whether you are choosing a reasonable prior distribution on theta or not. If you choose a completely weird prior on theta, then the model will end up generating kind of data that you would never expect in your experiment, right. So, this is a good test. So, how do we do a prior predictive check? Well, we go in iteration. So, let us say for I in 1 to 1000, let us say 1000 iterations, right. In each iteration, you sample a theta, sample a value of theta from its prior distribution. okay, and then conditional on that sample, you generate or you generate predicted data from the model, from the binomial, in this case binomial distribution, because that was our assumption, conditional on theta star, that particular value of theta, right. So, this will give you 1000 prior predictive samples. So, 1000 samples of data from the prior predictive distribution. Okay. Next thing you can do, basically next thing you need to do is, once you get the data, okay, once you have the data, you will calculate the likelihood function and the posterior distribution. Okay, basically you estimate the parameters. Okay, so you can call it the parameter estimation step. Okay, parameter estimation. How do you estimate parameters? Using Bayes theorem. So, the posterior distribution of theta given the data is likelihood of theta given the data prior distribution of theta divided by marginal likelihood. Okay. Now, there are different approaches to compute the posterior distribution. We saw a simpler approach that you take lot of values of theta, let us say between 0 and 1, and for each value of theta you compute likelihood prior and multiply them, so that you get unnormalized posterior distribution of theta given the data, right. And once you get unnormalized posterior distribution, you can sample from this distribution to get samples from the posterior. Okay. And that step is important, because once you have samples from the posterior, you can then do model comparison, posterior predictive checks, and many other things. Okay. In this step, you will also compute 95% credible interval. So, 95% range of your posterior distribution. Okay. Okay. So, this is parameter estimation step. So, this 95% credible interval will tell you that, let us say 95% credible interval comes out to be A B. Okay. So, basically it will have, it will be range between A and B. So, this range is actually, this tells you that the true value of parameter theta lies between A and B, and we can say this with 95% certainty. Okay. So, it shows your degree of certainty, that with 95% degree of certainty, you can say that the true value of theta lies between A and B. After parameter estimation, now you can generate posterior predictions from the model. Okay. So, posterior predictions. How do we generate posterior predictions? We sample a value of the parameter from its posterior distribution, the posterior distribution that you have estimated, right. Posterior distribution of theta given the data that you have observed in your experiment, and then conditional on that theta, you can now simulate new data from the binomial distribution, the assumption about how the data are generated, right, given this theta star from the posterior distribution, right. So, this will give you posterior predictive samples in the same way as you collected prior predictive samples. Okay. Now, the final step is model evaluation or model comparison, because up to this point what you have done is that you estimated that what values of theta might have generated the data and obs under the assumption that an obs comes from binomial theta and theta has this prior p of theta. Okay. So, whatever you have inferred so far is under these assumptions, under your likelihood and prior assumptions. But what if your assumptions are not correct, or your assumptions are really far from the true generative process, right? In order to do further inference, you need to compare your assumptions against some competing set of assumptions. Only then you can make a claim. Okay. You cannot make a claim about how good is your model, or about evidence, or about whether a hypothesis is true or not, without comparing it with some competing assumptions. Okay, that's not possible. Okay, so there is a saying that all models are bad, but some are useful. Okay, so basically both your models are not true generative process. They might be really far from the true generative process, but if you have two competing set of models, then you can at least compare them to check which one is closer to the truth, right? And that's a very important thing to do, because if you have just only single model, you cannot claim that this whether this was good model or bad model. Okay, you can only claim if we compare it to some other model, and then you can say that, well, this model is better than the other model. That's the only claim you can make, right? So in this step, you compare your model. So what was your model, original model M1? An obs comes from binomial theta, where theta comes from p of theta, against some competing model. Now this competing model can differ in terms of either likelihood assumption or prior assumption, right, or both, right? So let's say you assume the number of correct responses, let's say, comes from a Poisson distribution, where lambda comes from p of lambda or something, right? Something like this. Or you can also have, let's say, an obs comes from binomial theta. So the likelihood assumption is same, but the prior on theta is different. So prior on theta is, let's say, g of theta or something. Okay. So let's say this is M3. So this is how you can have competing assumptions and you compare them, and then based on that you make some inference. So this is the whole workflow of Bayesian modeling. Now how do we implement this in R? Okay. So let us take a quick example, an example about number of correct responses, and let's see how do we implement this in R. Okay. So your likelihood assumption is this, that number of correct responses comes from a binomial distribution with underlying probability of correct response being theta, where theta has a beta 90-10 prior. Okay. And let's say your data is something like this. You observe that there are 45 correct responses out of 50 trials. Okay. So let's say this is your data, or rather than 45, let's say 43. Okay. So 43 correct responses out of 50 trials. So this is your data. Okay. Now let us go with it. Let us implement the whole Bayesian workflow. What is first? We specify the assumptions. We specify the assumptions, model assumptions. What are our model assumptions? Well, they are given here, by the way. So this is our likelihood assumption and this is our prior assumption. Okay. So we have a specified model assumption. So step 1 is done. What will be step 2? Once you have specified model assumptions, you can generate prior predictive distribution. You can generate prior predictions of the model. So what does the model predict even before seeing the data? And this could be a good check whether your priors are reasonable or not. So how do we generate prior predictions? Okay. So let us say I create an empty data frame. Okay. So df dot prior pred. Okay, it's an empty data frame with how many columns? So we need a sample ID. Okay, we need then a theta, and then we need corresponding prediction, right? So let's say 3 columns and number of rows 0. So you want to create empty data frame with 3 columns. You can name the columns as well. So the columns are named sample ID, theta, and ypred. Okay, so this is the predicted number of correct responses. Okay, so this is how the columns are named. All right, now we determine how many samples do you want. Okay, so let's say we start with 1000 samples. Okay, 1000 samples from the prior predictive distribution. Okay. So basically, we will draw 1000 samples from the prior distribution of the parameter, and then corresponding to each sample, we will generate a prior predictive sample. We will generate, we simulate data with as many observations as are there in our sample size, right. So what is our sample size here? We had total 50 trials, right. So you can write that. So number of observations, or let's call it sample size. Sample size is 50. Yeah. All right. Now we iterate through all these samples. Okay. So for I in 1 to number of samples. Now corresponding to each sample ID, we will simulate a theta. Okay. So let us call it theta I. And how do we simulate it? We simulate it from its prior. So what was the prior? Beta prior. So R beta, we want one sample from the beta prior with shape parameters 90 and 10. And conditional on this theta, we will simulate from the likelihood assumption, which is binomial. Okay, so we'll generate data from binomial distribution. Okay, with sample size. What is the sample size? 50. Sample size 50, and underlying probability of correct response will be theta I. Okay, so that's how we will generate. We will simulate data, right? And now we can store all this in our prior predictive sample, right? So overall prior predictive distribution, right? So df prior pred, we can r bind. Okay, so r bind df prior pred. We have done something similar in the previous lecture. So data frame. Okay, so in the data frame, sample ID is what is the sample ID here? I, right? Sample ID is I, theta is theta I, and y pred is y sim. By the way, this thing is slightly different for binomial likelihood. If you would have, let's say, a Gaussian likelihood, then each prior predictive sample would have basically n obs number of observations, let's say 50 observations. But here, because of the property of this distribution, all you need to care about is that how many correct responses are there. Okay, so that is the simulated data. Okay, so it's all fine in that sense, right? However, you can change this. You can change the same problem a slight bit. How? So rather than talking about total number of correct responses, let's say if you want to model whether in a particular trial the participant would produce a correct response or not, whether they would produce 0 or 1, then you can assume rather than binomial that comes from a Bernoulli distribution. Okay, in that case, all this thing will become similar to a normal distribution where for each observation, for each trial, you would have an observation 1 0 1 0 1 0 like that. Okay, but it's okay for our purpose here, so this will work. Okay, so now we will have our prior predictions using this. Okay, so if you want, you can visualize your prior predictions. So for example, hist of df prior pred y pred. Okay, and this is how prior predictions look like. Okay, now comes step 3, that how we There are of course many other ways to visualize these prior predictions we have seen earlier in the previous course, but so you can take a look. For example, you can generate summaries of each prior predictive sample. Okay. Now step 3 is parameter estimation. So how do we estimate model parameters here? Well, one simple method that we know so far is that we take a lot of values of theta from 0 to 1 and length, let's say 10,000 values of theta, and corresponding to each value of theta we calculate likelihood. Okay, how do we calculate likelihood? Using d binom, because that was our likelihood assumption. What is data? Data is 43, right? So let me write the data here. So n obs is 43. So you need to use n obs here. Okay, and so n obs, sample size is sample size, right, and the underlying probability being theta, right. So this would give you likelihoods. So this would give you 10,000 likelihoods corresponding to each value of theta, and then you can calculate prior density corresponding to each value of theta using d beta, because that's our likelihood assumption, right. So corresponding to each theta, it would look like this: 90, 10, right. So that's our prior, and if you want you can plot them together, right. Now we want to calculate posterior, so at least unnormalized posterior. Okay. So unnormalized posterior would be likelihood into prior. This would give you unnormalized posterior distribution corresponding to each value of theta. Okay. Now, in order to draw samples from this posterior distribution, you can use sample function. So let's say you want to draw 1000 samples of theta from its posterior distribution. Then what you can do, you can use sample function, draw from this vector theta how many samples you want, 1000, depending on, so weights will be determined by weights, basically each sample is weighted by its unnormalized posterior density. Okay, and replace, keep replace equals to true. So this will give you samples from the posterior distribution, and if you draw a histogram of the samples, this would look like posterior distribution of theta. Okay. So this was step 3. Now once you have these posterior samples, you can draw posterior predictions. Okay, how do we draw posterior predictions? In the same way as you draw prior predictions. So I will just repeat the same code, but rather than drawing from the prior distribution, now you just need to draw from the posterior distribution. So you just need to change this part. So theta I does not come from r beta, rather it comes from your prior distribution. How do I sample from prior distribution? So let's say I draw one sample each time using sample function from theta, weighted by unnormalized posterior density, right, and you can keep replace equals to true. Okay. So this would give me a theta every time from its posterior distribution. Okay. All right. Now you can do other things. For example, you can check how you can compare these posterior predictive samples against the actual observed sample, right? So just to check how reasonable is your likelihood assumption. Okay. Once you have these posterior predictions, the step 5 would be model comparison. So, you compare this against a competing set of assumptions. This step I haven't taught you yet. So, this we will come to this part later on towards the end of this course, basically towards later half of this course, but that would be a very important step to do here. So, this was model 1, now you compare it against model 2. So, model 2 will do all these same things. Basically, you will specify its likelihood prior assumptions, generate prior predictions, estimate parameters, generate posterior predictions, and then you can compare model 1 and model 2. So, this is how you can implement a whole Bayesian model in R, right. So, this is it for this lecture. In the next lecture, I will discuss the concept of Bayesian learning, that how does a model learns from data iteratively, okay, and how what impact does it have on a Bayesian model, and what does Bayesian learning mean actually, right? You might have heard this term. Okay. So, the next lecture we will discuss Bayesian learning, and after that we will discuss how to specify prior assumptions for your parameters of interest. Okay. We will of course again discuss the idea of prior assumptions later on when we do regression modeling, when we apply this on some actual examples. But in next to next lecture, we will discuss it at least conceptually, that what does it mean to specify prior assumptions. Okay. All right, so we will stop here, and we will meet in the next lecture to discuss Bayesian learning. All right, thank you.